Okay, so we've looked a little bit about what the cost of solar. We've defined the air mass. We looked at the amount of solar installed. We looked at a few little applications and some of the history. Now let's look at the technology itself. So it's very difficult, again, to kind of visualize exactly what's going down at this very small scale. You hear all the funny little electron orbitals. More or less what's happening is when a photon comes in, it's going to take one of these electrons from its ground state, or its most comfortable or least energetic or at equilibrium. The photon comes in, and it's going to take one of these guys and kick it up to a higher level. The weird thing about photons, electrons, the quantum world is that there's no sort of in-between levels, if you will. You're either in one place or another. And I don't know if any of you are musicians or not, but if you think about sort of strumming a guitar string, it's going to have like a single mode of vibration and then a higher mode, a third mode. There's no sort of in-between modes, if you will. Just like on the periodic table, there's no element in between oxygen and fluorine. They're discrete because the particles that make them up are discrete and quantized. So same thing here with these energy bands. Photon comes in, kicks an electron up to a level. Once that photon has been absorbed, that electron is going to want to come down somewhere. And if there's an electrical load on the circuit, that electron is going to go where it's most needed. It's going to go to make some heat or make a motor or whatever. So I think this is and so there's no real ramp. The car, the car is an okay analogy, but you never saw the car like drive up the ramp and then drive back down. It's either in one place or the other, and that's kind of the weird thing about the quantum world. But once this thing is up in the so-called conduction band, it's now conducting. It's doing work for the circuit, and it'll come back down eventually, end up in the valence band, and be ready to do some work again as soon as that next photon comes in. Does that make a good enough analogy with what's going on? So they're kind of showing you on a gravitational scale what's happening when the photon comes in and smacks the junction. Okay, so that's just kind of a macro scale analogy. Let's now dig down into the PV cell itself. And as I mentioned before, silicon has 4 valence electrons. It's got 4 electrons in that outer shell that's more or less sharing with its neighbors, right? So let's go back again here to that periodic table. And here's silicon. So focus on that 3p shell. There are 6 available slots there in that 3p shell. And a way to visualize it, you can see that this sort of blue and gold dumbbell, if you will. If we kind of move out a little further, we'll see that these shells get filled up. And if we move all the way out to argon, there's sometimes a way to, this isn't a bad way. See how this in phosphorus, the thing's kind of going left and right, sulfur's kind of up and down, and chlorine's kind of back and forth. That's one way to visualize this atom three-dimensionally. It's sort of 3 orthogonal dumbbells to each other. Argon gets a little bit weird, but you can see by the time you get to argon, all of those 3p shells are filled. But since way back here at silicon, there are 4 empty or 4 empty slots in that particular shell, it can have these 4 neighbors. And so this depiction, this sort of cartoon depiction, is not that far from reality in terms of how these silicon atoms are actually arranged in a crystal lattice. All right. So what's going on here? Each of these two little dots actually are two little electrons, and they're most stable in pairs, one with what's called a spin-up property, and another with a spin-down property. And you can think of them like two little magnets, and a lot of times, two, like a north and a south magnet will attract to each other. So they're happiest, most energetically stable in those pairs. But if we look, this little arrow, so let's look at figure A. So pure silicon has a cubic structure shown in 2 dimensions for simplicity. So 4 neighbors, obviously. Silicon atoms has 4 valence electrons. I just said that. Each is held in place by sharing the 2 electrons, those are small red dots I just mentioned, with each 4 neighbors at equal distance. Occasionally, thermal vibrations or a photon of light will spontaneously provide enough energy to promote one of the electrons into the conduction band, which I just mentioned, where the red dot is free to travel through the crystal and conduct electricity. So this could be thermal. It could be a photon coming in and smacking it. Okay. Now in B, so that's pure silicon at the top. Now in B, what we have is it's been doped with phosphorus. The phosphorus has 5 valence electrons. So I guess what they're trying to show here is this little electron that's was in that open circle is now kind of cruising around in the lattice. In the case of the phosphorus, there's already that extra electron sitting there. So let's go back to the periodic table. So here's silicon. Here's phosphorus, and there's that extra electron I just mentioned. It's sitting right there on the periodic table. It's also sitting kind of right here, hanging out. I sometimes think of musical chairs. The music stopped, and there's that one extra electron kind of left hanging out, and it's free to run around. No seats left, sorry, but you're welcome to conduct electricity. So that's an N type. N stands for negative. The electron itself is negative, so that's where you get that extra N, or that extra negative charge. All right. You can also have a P-type crystal. This has been doped with boron. So let's go back here, and here's boron. And you'll notice it's just got that one lonely little electron. So it's kind of sucking off that other, well, not extra, but it's sucking off one of the electrons from silicon. So you see that boron here, and hey, there's nothing there. I'm sort of missing that electron. And the way to think about that is in the next figure. But just kind of keep that in mind, and keep in mind the fact that it's positive. So the fact that it's missing an extra electron means that the additional proton in the boron nucleus makes that thing positive, or a P-type semiconductor. All right. Now, here's the actual physics of what's going on. So you've got a P-type silicon, and that's labeled as the big green part down there, with a thin layer of N-type silicon on one side. So a photon of light with the appropriate amount of energy, and again, not every wavelength. We looked at the whole spectrum, and this is a challenge in solar cells. How do you tune them so that they're actually getting the maximum amount of energy in? Some are reflected, some are transmitted, some are absorbed. Really what you want to have to happen is the maximum number of absorption, just like we had in our solar thermal. You want those electrons to actually interact, like it just did here in number 1. Number 3, that thing got transmitted, does us no good. Number 4, it got bounced off and it got reflected, does us no good. So the more electrons that can come in, the better. Okay, So let me just read here. The photon of light with the appropriate amount of energy penetrates the cell near the junction of the two types and encounters a silicon atom. So the photon actually hits the silicon atom. That's what's happening in number one. It dislodges one of the electrons, knocks it up into a conduction band and leaves behind a hole. The energy required to promote the electron into the conduction band is known as the band gap. So, another way to think about that back on this guy is just basically getting from this energy level up to another energy level. It's just known as the band gap, the energy to hop up there. And we'll look at that in figure 312 in a little bit. The electron, thus promoted, migrates into the layer of the n-type. So you can see it going from here right into that n layer. And the hole tends to migrate into the p-type. So the hole heads off in this direction. And again, this is a metal, so all of these atoms are sort of sharing these electrons and holes. The electron travels to a current collector. That's what these guys are. And if you remember seeing the silicon cells either outside my office or in the back, those are just basically the silver solder that's on them, the little wires, making completing the circuit. It will then re-emerge, so it'll actually travel through the circuit and then come back. So there's still conservation of matter. I mean, the electrons are actually flowing this thing. They're just sort of getting, kicked up into this level, flow through the conductor, and then back down and sort of annihilate or fill in the holes that are migrating in the other direction. So you have electrons go in one direction, holes go in the other, and then they finally meet back up at the current collector at the bottom. So there's your circuit. There's your loop. Any questions on that? It's a little tough to visualize sometimes. Sometimes you're like, what the heck? I've never seen an electron in my life. What the heck is a hole? Well, a hole is just where an electron used to be. There are some pretty cool atomic force microscopy images if you're interested of actual atomic lattices. I mean, we can actually physically see these things and touch them now. So it's real. It's happening. It's there. All right. So let's look at the next one. So I just mentioned the energy gap or the band gap. The valence bond, this is more or less where the electrons are most comfortable in the stable material. And so sort of a side view. In comes the photon, kicks that electron up where it was not before, leaves behind this so-called hole. And then once it's there, one way of looking at it is just having the electron sort of rolling back down into a lower energy band. The holes are sort of floating upwards, and then they recombine, and everything sort of restabilizes. Now, as you might have guessed, there's not just one single type of silicon wafer. The one that's being shown here is more or less a monocrystalline, and that's more or less what we've been looking at so far, where you just get one giant sheet of silicon crystal. Very expensive, more efficient, and that's what we're going to see in some of these space-based applications. But here's more or less how the thing works. You start out with just regular old sand. It gets cooked. It gets hot enough that the oxygen actually comes off. It's not allowed to interact with any more oxygen, but it's heated to the point where the oxygen leaves. The silicon is more or less now in a pure form. It is dissolved in hydrochloric acid. So this is really getting it down really to the atomic level. I mean, you don't want silicon binding with silicon in some other way. I mean, you're really trying to get this to just as pure as possible silicon. All the oxygen's out of there, all the other metals are out of there. So you're cooking all that stuff off. Now you're going to dissolve it in HCl. So you're really getting right down to the atomic level. Trichlorosilane, that chlorine, if we take a look at the periodic table, it's sitting way over here. It's just got that one open electron there in the 3p. So it's going to bind very tightly to just about anything. It's going to form what's called an ionic bond. Okay, and now we're going to reduce it with H2. So the H2 is then more or less going to pull off the chlorine that got it down to the atomic purity. And now we're going to heat it at 1500 C, and I still don't know exactly how to pronounce this, but the Kowalski process. And this is more or less taking this and just growing a crystal in a furnace at high temperature. And one way to think about this is, I don't know, imagine you had like a box of pencils and you wanted them to align. If you shook that box long enough, they're all going to sort of lay down in their tightest packing possible. If you shake them really hard, they're going to fly apart. But the whole idea behind crystal formation, and you've probably seen ice crystals form on a pond where it's very close to 32 degrees. You get these nice big crystals where if things freeze kind of quick, you'll get a lot of really small ones. So the idea in the Kowalski process is you've got at just the right temperature for just the right amount of time that it forms this giant, beautiful crystal, just like you'd see ice forming on a pond at a temperature very close to freezing. We're sort of at that freezing temperature for a long time. That's more or less the best way to describe it. It's kind of a high-tech cooking class. So after that crystal has formed, they are then sawed, and actually you're losing some of your material there. We talked a little bit about embodied energy this morning in my other course, and here's where it is, man. These are some high temperatures. Then they're polished. Then they are doped. So this is all the boron and the phosphorus are introduced in a highly controlled manner. Anti-reflective coating. Why do you want that? Well, so that as many photons come in as possible. You've got your front contacts. These are actually the metallic conductors to allow electricity to flow, and then connecting, soldering, et cetera, put them in an array, test them, and let them rip. So a lot going on in to make one of these guys. All right, so that's single crystal technology, and we'll take a little break.